Hello, wonderful people. In this slide, we're going to do two problems that are straight out of the momentum homework. And I'm going to show you every little thing and every little step along the way. Okay, so we have a 20-kilogram fish swimming in the ocean. She's hungry. A 5-kilogram fish swims by. Dinner time. The 5-kilogram fish is looking up, thinking, "What a beautiful day to be a fish in the sea." He is daydreaming and comes to a stop just as he's looking up into the sun. The 20-kilogram bigger fish gets up to speed at 10 meters per second. She's a fast fish, and then glides in and eats the 5-kilogram fish in one gulp and glides away. That fish there in the picture is a grouper, and the fish is stating that his family name is Gruber, but the name of my species is Grouper. We travel in groups, so groups of Grubers. Ah. But I wanted to show you this so you can see what I'm talking about with this example. One fish eating another fish.
We're getting close to the end of our dive, and to be able to observe these animals in their natural habitat feeding is pretty remarkable. Oh, big grouper.
Oh, the Gruber's got a shark. What?
What?
Zoom out.
Oh my gosh! Oh my gosh!
The Gruber used us as cover. Shark.
What?
Yes, that has a whole shark in its mouth.
No way.
More evidence, really, of how these systems work.
Okay, so now that you understand the setup for the problem, a jury physics student, not named Steve Tishner, is in a glass-bottomed boat and saw the whole thing. She diagrams it in her physics notebook, and it looks like this. There's the picture of the fish going at 10 meters per second, and the little fish standing still, 0 meters per second. Their weights, 20 and 5. That's the before, or initial, and then the final setup is on the right. So we've got one 25-kilogram fish, and the question before the court is, how fast is that fish moving? Using the law of momentum, we can answer that. So how can we use what we know about momentum to find the speed of the 25-kilogram fish in the picture on the right? Kind of just said that. The law of conservation of momentum can be simply stated as initial momentum equals final momentum. So I'm going to abbreviate B for big fish and S for the small. And now we take both fish into account. Initial of the big plus initial of the small equals final momentum of the big and final momentum of the small. Same equation. Now P equals MV, so I can substitute in MV for all the P's, which I do in the parentheses there. Then I'm going to take that equation, and there it is again. And just to make everything perfectly clear, we can then split up all the M's and V's, so every variable has its own subscripts. So M and V are the variables, and the subscripts are the B's, S's, and I's and F's that tell us which mass and which velocity we're talking about. So in the bottom equation, reading left to right, I have the initial mass of the big fish times the initial velocity of the big fish plus the initial mass of the small fish times the initial velocity of the small fish equals the final setup. The final mass of the big fish times the final velocity of the big fish plus the final mass of the small fish times the final velocity of the small fish. That's that same equation at the top. Now we can look at this equation and think about what we know. What do we know? We know the masses of both fishes, and we know the speed of the big fish before she ate the little fish. So the initial speed of the big fish is 10 meters per second. Now we can look at that equation and think about what we know. What do we know? Do we know anything else? Well, yeah, we do. There are two tricky things we also know. So of the two tricks, here's the first one. We know that the final mass of both fishes is combined because the big fish ate the little fish. This also means that they are now traveling at the same velocity. So if the little fish is inside the big fish, they're traveling at the same speed. We know that the final mass of both fishes is combined because the big fish ate the little fish. Right, that's that same text. This also means that they are now traveling at the same final velocity. So that equation on the first equation there becomes the second one. And I'm going to show you exactly how that happened. So there's the first equation. And on the left, it's mass times velocity of the big plus mass times velocity of the small equals mass times velocity of the big plus mass times velocity of the small. Now, if you see in the green, I've got the velocity of the big fish at the end of the problem and the velocity of the small fish at the end of the problem. Well, because those two, the big fish ate the little fish, those velocities are the same. So I'm going to combine those into the velocities there. That's where I bring them down from the green arrow, since that's the exact same velocity. So now I just do a little bit of algebra, and I still have the masses added up inside the parentheses times the velocity of both. So do you see how I took the two v terms in the final part of the equation and combined them into one v term? Okay, do we know anything else? There's the second tricky thing. Second, we know one more thing. We know that the initial velocity of the small fish was 0. And since mass times 0 is 0, we can eliminate that term. Let me show you how. So there's the equation where we combine the two velocities. That's still on the right. But on the left, we have the mass and velocity of the initial for the big fish plus the mass and velocity for the initial of the small fish. But we know that the v sub si, the velocity of the small fish at the beginning, was 0 meters per second. So if you plug in 0 for v sub si, then 0 times the mass is still 0. So that term just goes away. So you can see I've got the vs going to 0. So if we eliminate that term, now we have the equation on bottom. M times v equals the part in color. Does this make sense? Good. So that equation at the bottom there, I just brought over to the top here. And we know 4 of the 5 variables in that equation that we're looking at. We do not know the green one over on the right. So we're going to solve for it. And here's how. There's that same equation from there to this slide on the top. And we're going to divide through by the red and blue terms. So we divide the quantity on the left and the quantity on the right, both by what's inside the parentheses. That's the second equation I have there. Now in the third line, I know that if you have something that's on top divided by the same thing on the bottom, well, that's always reduces to 1. So those two terms go away. So now on the bottom line, I've got my green term on the right, the velocity final, which is what I don't know, and all the stuff that I do know is on the left. And that's just good old-fashioned algebra. Are we okay with that? Okay, moving on. I'm going to take that equation at the bottom, and there it is at the top. Now, this is what I call plug and chug. I've got velocity final equals all that stuff. So I plug in the information, and then in the second equation down, and on the far right, I plugged in the numbers. 20 kilograms, 10 meters per second, and then the mass of the big fish is 20 plus the mass of the small fish is 5. So then in the third equation down, I just did the simple math. On the top, I multiplied 10 by 20, and on the bottom, I added 5 and 20. And I can do that because the 5 and 20 are the same units. They're both kilograms. Now, if you look on the bottom equation, I now have 200 kilograms times meters per second divided by 25 kilograms. So the kilograms cancel, and if I divide 200 by 8, don't don't be afraid to break out the calculator. Then I get 8, and then I'm left with meters per second. Now, does this make sense? 8 meters per second? Well, I'm looking for a velocity, and velocity is measured in meters per second. So that's one hint that I've got right. I've got the units right over here, meters per second. And then the second thing I would say is, does 8 sound right? Well, the velocity of the big fish was initially 10, and now it's 8. So she slowed down a little since she took on the extra weight of the small fish. That kind of makes sense, right? I mean, if this answer had been 800, that would make me want to check my math. But at this moment, I think we're okay. So there we are. Ta-da! So there's the grouper with the baby shark still stuck in its mouth. And according to that problem, we now know she is traveling at 8 meters per second. Congratulations. Now we're going to go on to the second problem, which is only just a little bit more complicated, but I'm going to do it in the same format where I show you every little detail along the way. Okay, here we go. Hello, wonderful people. Now we're making it a little harder. The 5-kilogram fish is looking up thinking, what a beautiful day to be a fish in the sea. She's swimming along at 5 meters per second. The 20-kilogram fish gets up to speed at 10 meters per second and then glides in and chases the 5-kilogram fish. The little fish sees the big fish coming and speeds up to 8 meters per second. Oh, at which point the big fish eats the little fish. So the big fish is moving at 10 meters per second, the little fish is moving at 8 meters per second, and that's when the little fish gets eaten. A Drury physics student, not named Steve Tishner, is in a glass-bottom boat and saw the whole thing. She diagrams it in her physics notebook, and that's what it looks like. The 20-kilogram fish is moving to the right, so is the 5-kilogram fish, and then afterwards they're eaten and they're just one fish inside another. Then the numbers are down below. The big fish is at 10 meters per second, the little fish at 8 meters per second. So what is the speed of the combined fish? All right, so do you remember when we did the review at the end of the first problem? Can I just say that you should be expecting an answer slower than 10, but faster than 8, right? Does that make sense just based on what we're looking at here? And the units are going to be in velocity, meters per second. Okay? So how can we use what we know about momentum to find the speed of the 20-kilogram fish inside a fish in the picture on the right? Oh, sorry, no picture. So law of conservation of momentum. Initial momentum equals final momentum. Then we're going to break it up into the big and the small fish, which is the equation at the bottom. And then now it's the equation at the top. And then P equals mv, so I'm going to take all the p's and substitute in mv, which I do it below. The mv's are inside the parentheses, and to keep everything perfectly clear, I'm going to distribute the subscripts to each m and each v. Oh, which I go from the top to the bottom there. So now I've got MBI, VBI plus MSI, VSI equals MBF, VBF plus MSF, VSF. We're good. This is just restating the law of conservation of momentum. P initial equals P final, only now we're applying it to the problem. Now we can look at that equation and think, what do we know? Well, we know the masses of both fishes. We know the speed of the big fish and the speed of the little fish for initial velocities. Do we know anything else? The one tricky thing that we know also carries over. We know that the final mass of both fishes is combined, and if you have both fish together, then they're traveling at the same speed. So that equation becomes the second equation on the bottom. Did I show you this? Yes, I'm going to show you that same, this is the exact same thing. I've got this as the equation for all the terms. I'm going to take my v, my velocity of the small fish and my velocity of the big fish. They're the same thing now. So those two combine into this term. And that means I take the mass and the mass, which were added, I put them inside some parentheses. Does this make sense? Why, yes, it does. Why? Because algebra. So now that's my equation. We know 5 of those variables. There's one we don't know. That's the one in the green. So we're going to solve for that. We're going to take that inside the parentheses and divide that on both sides of the equation. This side cancels out. And so now we have that green part that we don't know. Oops, that green part that we don't know equals to all this. And we know every single one of these terms. So we know every single one of these terms. And now I'm just going to plug it in. So my final velocity equals my mass of the big initial is 20 kilograms. My velocity of the big initial is 10 meters per second. Plus, my mass of the small fish is 5 kilograms, and my velocity of the small fish is 8 meters per second. Divided by mass of the big fish, 20, plus mass of the small fish, 5. So now I'm going to take this 20 and 10 and multiply together for 200. 5 times 8 is 40. I can add 20 and 5 because they have the same units, so I get 25 kilograms. Now, do you see that this 20, 200 kilograms meters per second plus 40 kilogram meters per second, these have the same units, so now I can just add these two together, and that's what I do in this step. So 200 plus 40 is 240. Now I've got 240 over 25, and then the units are kilograms over kilograms, so those can cancel, and meters per second. So 240 divided by 25, that's a little tough to do in your head. Oops. It's 9.6. I double checked that. Meters per second. 9.6 is between 8 and 10, so that's in the right ballpark. And meters per second is a velocity, which is what we're looking for. So I think we're good. Ta-da! All right, now we are really done. The only trick I have, the only trick I have you will see in the homework. Oh, the only trick I have you will see in the homework, and that is to make one of the velocities in the opposite direction. So I have the fishes swimming towards each other. So that just means that you have to have the sign on one of the fishes. So the fish going to the right, you'll call that positive, and so the fish going to the left will have a negative velocity. That's one of the last problems. The first few problems are just like the ones we did here, and hopefully those will go pretty easy for you. Hopefully. Now, I know that going through this stuff, it's hard to get used to the language. So if you're just not sure about something, please give me a call, shoot me a text, or an email, and I'm happy to help. All right, good luck. Thanks for everything. Bye-bye.